Alright people, good evening and welcome to Analog Electronic Circuits. This is lecture 8. In the last class we were discussing the practical problem of biasing a transistor with a gate source voltage. So, what we had was something like this. Again, as far as the biasing is concerned, the resistor in the drain is of secondary consequence, right. If you assume that the VDD is sufficiently large, then and this is R2 and this is R1, this is equivalent to taking a battery of voltage Vg, let me call that Vb, is VDD times R1 over R1 plus R2 and connecting it to the gate like this, and of course, this goes to a sufficiently large VDD. Now, what are the problems with this arrangement? Yeah, so problems with changes in VDD as well as V threshold, and it also goes to say that since threshold voltage is a function of temperature, now if the temperature changes, the ambient temperature changes, then the threshold voltage changes, but the gate bias does not know anything about the threshold voltage of the device, and therefore, the operating current changes, and then with it the GM and all the other stuff. Okay. So, this therefore is problematic in practice. Okay. And we saw last time that this can make the current either much too large or much too small. Again, that depends on the change in the threshold voltage. So, the problem therefore is to figure out, the root cause of the problem we already discussed at the end of the last class, and that was that the gate bias voltage Vb, you can think of it as some kind of a dumb battery, right. It does not change voltage when the threshold voltage or the mu and Cox W by L of the MOSFET changes or deviates from the nominal value, and as a consequence the quiescent operating point is changed. So, the fix therefore is to make Vb intelligent and be able to figure out. So, basically the question we need to ask is the reverse of what we have been doing so far. So far what have we been doing? We are saying here is a MOSFET whose properties are known, right. I apply a voltage Vb, tell me what the current is. Now we have got to ask the reverse question, namely I want a current which is I do not know, maybe 100 microamperes, 200 microamperes, whatever. I need a current Iref inside, flowing through the drain. What should be the gate source voltage that I should apply so that the current in the drain is fixed, all right. So, if I answer that question, then I will be able to hopefully build a circuit to do the same thing, and that basically will ensure that regardless of what the ambient temperature, what the threshold voltage is, you get the desired current Iref in the drain, right. So, in other words, imagine you are in a lab, okay. You have all the laboratory instruments, ammeters, voltmeters, voltage source, current source, whatever, and you have a MOSFET whose threshold is unknown. All right. Mu and Cox W by L is also unknown, all right. Now, the question that I am going to ask you is, how would you, what what would you choose? How would you come up with this battery voltage, right? Or what would you apply at the gate terminal so that the current in the drain is some desired current Iref? What would you do? In principle, what will you do? So basically, what the principle is the following. That is, you therefore at the gate you have to have a variable voltage source, correct? Okay, and what are we doing? We apply some voltage source, unknown voltage, to the gate. Note down the current. So note down the current is equivalent to saying that you measure the current in the. What is the meaning of noting down? I mean, you basically have to measure the current. Now only then you can note it down, correct? So what do? You need to stick an ammeter into the drain. So basically, but we have to ensure that the transistor is operating in saturation. So we hook the drain up to a sufficiently large voltage so that the transistor is known to be operating in saturation. So basically, then we have an ammeter which shows some reading, right? And that ammeter will be reading ID, correct? So we apply some Vg and we read some ID. Okay. Now, if ID is greater than Iref, what does it mean? Yeah, let us say the magic voltage at which the drain current is ID is some Vg star, right? So this is ID equals Iref. So if ID is greater than Iref, it means that the applied voltage at the gate Vg, is it too much or too little? Is greater than Vg star. So what must you do? Must reduce Vg. Does it make sense? Right? On the other hand, if ID is less than Iref, what does it mean? It means that the gate voltage is too little and therefore I must increase Vg. Does it make sense? So eventually when you are done, what happens? The gate voltage will be Vg star and the current will be equal to Iref. Okay, all right. So what is that Vg star? It's Vt plus square root of 2 Iref over mu n Cox W by n. All right. So just to take a step back, what have we done in this whole process? We did not know, please note that we did not know either mu n Cox W by L or Vt, but still we have managed to find the exact voltage needed at the gate to be able to make and to ensure that the drain current is equal to Iref. Okay. Is this the only way of doing things, or is there another conceptually different way of doing things, right? Which is, we don't know the properties of the MOSFET. What numbers are we, I mean, when we say properties of the MOSFET, what are we looking for? The mu n Cox W by L and Vt. Okay. So, is there an experiment? Is there an experiment you can do to measure mu and Cox W by L and Vt? You plop in two voltages at the gate, measure the currents, and solve the equation. Correct? Okay. So, once you go solve the equation, let's say now you know both mu and Cox W by L and Vt. Now, if somebody says this is the IREF I want in the drain, what will you do then? You have these mu and Cox W by L, you have Vt, you go and do the math, and then it will tell you, Vg star, and that voltage that you must put must be 1.234 volts. Go and put that, stick that voltage in there, and that will also give you Id equal to IREF. Now, if the temperature changes, right, or the device changes, what do you have to do now again? You again have to make measurements, again extract mu and Cox W by L and Vt, again do the math, and then find that Vg, right? Or God forbid, if you don't know how to solve the equation properly and you made a mistake and you missed a decimal point, okay, then what happens? Well, you put some, I mean, you've gone and done the math, you've been careless, you go and put that voltage there, and the current is going to be completely off. You understand? Okay. So, these are two, I mean, the first method where we, put in a voltage, keep monitoring the current and tweak the gate voltage until the drain current is what we want, is what is that whole mechanism? It's not trial and error. I mean, trial and error is basically I will put in some voltage, measure the current. Okay, well, it's not what I want. I'm going to put in another voltage or a randomly chosen. Okay, that is trial and error. What we are doing is not trial and error. It is feedback. I hope that you know the difference between trial and error and feedback. Okay. What we have on the board is basically feedback, where we compare what we have with what we want to have and kick the the system, in this case the MOSFET, in the right direction, so that what you want is the same as what you have. All right. Okay. The approach where you basically go and find mu, I mean, either you find mu and Cox W by L and Vt by using measurements or looking at the data sheet, basically, and then doing the math and then putting that voltage between the gate and the source. That is not feedback, it is an open loop method of doing things, right? Which is more robust, right? Because in the open loop technique, any error you make in either reading the data sheet or computing the computation, basically, I mean, there's no way to figure out whether the what you actually achieve is what you wanted to achieve. Correct? To give you an analogy, okay. So, if you want to go from I don't know, here to the electrical engineering department, there are two ways of doing it. One is to put it in Google Maps, right? And what does Google Maps tell you? It will basically say, walk, I don't know, I mean 50 feet and then, climb down, 20 feet and then walk another 300 feet and then make a left and then walk another 400 feet and then you make a right and then, that will be your, that will be the electrical engineering department. Okay. Now, if somebody who's doing data entry has made a mistake, okay, then what happens? You walk instead of 50 feet, maybe it is 80 feet and then, you're trying to walk and then you jump off the parapet, okay, because Google told you to do so, okay, you understand, all right. And likewise, if any of these measurements are in error, right, either because your GPS is not working or, there's a error in data entry, all right, then an open loop technique, as you as you can probably understand, will basically lead to errors, right. On the other hand, the other way of giving somebody directions, which is the more natural way of doing it, is to say, keep walking, find the first step of first flight of stairs, go down 2 flights, then keep going straight, right, and the first building you will see is ZSP. Okay. Now here there is no notion for, there is no notion of accuracy, nothing, right. So you keep walking, and the first landmark you are looking for are the stairs. So you keep walking, and at every point in time you are measuring the error between your location and the location of the stairs. That's what you are doing, right, though you may not realize it, correct. Okay. And then you find the stairs and then keep going down and so on, all right. Now since you're used to Google Maps, you think that this open loop stuff is okay, but most of what we do, right, in daily life is all governed by feedback, right. For example, even as simple a thing as taking a spoon and putting, taking food from your plate and putting it into your mouth, okay. The Google way of doing it would be to say, well, apply 3 Newton meters of torque on the spoon and lift the stuff up, and then go up for I don't know, 32 centimeters, and then make an angle of 46 degrees, and then push the spoon towards your mouth. And if any of those numbers are wrong, it will be like that Charlie Chaplin movie Modern Times, where the stuff comes and hits your face. All right. So close to, but every day when we are eating, we are never making any of these calculations, right? Whether the spoon is heavy or light, whether the food is dense or not, whether your eyes are open or closed, right? Miraculously, the food reaches your mouth without any error, right? Why is this? See, at every time you are basically sensing the difference between the position of your mouth and the position of your hand, and making sure that the tip of the spoon enters your mouth, right. Now, if you don't believe me, you try to close your eyes and then try to feed a friend, okay. So you can see that everywhere where you want robust performance, right, independent of within quotes device characteristics, right, namely the spoon, namely the kind of shoes you're wearing, right, okay, all that we basically independent of all these device characteristics, robust performance is often only possible through the use of feedback. Okay, like in this experiment, the properties of the MOS transistor were completely unknown. I just gave you a 3-terminal device and said, go figure it out, right? And quite naturally we did. Okay. So everything robust, in circuits as well as in the world is all because of negative feedback. Okay. So now we know the basic idea. The next job is for us to translate this into a circuit. That's easy enough. Once you figure out, once you know what you want to do, doing it with circuits is easy enough. So now let's get to that. So what are we trying to do? We need to compare, therefore, we need to compare the current in the transistor ID with the drain current, with the desired current I ref. What is the meaning of comparison? What is comparison? It's subtraction, right? So when you compare your marks with the neighbors, you're basically saying, I got 2, he got 4, right? There's a problem. So comparison is nothing but subtraction, right? So you want to compare currents, so you want to subtract currents. So what physical principle will we use to subtract currents? God given KCL, right? Okay. So if you want to subtract 2 currents, it's very straightforward. You make the 2 currents fight, and then the difference will come out. So therefore, we want to compare a reference current. So let's assume that the reference current is available as a current source. Okay. All right. And we want to compare the reference current with ID, the drain current of the transistor. So, what comment, how do we subtract these two currents? How do we get the difference between these two currents? Yeah, you connect the two together, okay, and this is ID. So, we apply some arbitrary Vg here, we do not know what, at this point we do not know what it is. So, there will be some ID in the transistor, and we compare it with IRF, and let us look at the potential of node X, right. If IRF is greater than ID, what comment can you make about the potential of node X? If ID is smaller than IRF or IRF is greater than ID, what comment can we make about the node potential of node X? A node is nothing but a small bucket which holds charge, right? Infinitesimally small bucket which holds charge. Okay. If more charge is pumped into a node and then is being removed from a node, what comment can you make about the potential? It will increase. Is that clear? Okay. All right. Then, so in other words, if IRF is greater than ID, Vx will go up. Correct? On the other hand, and what does this mean? If Vx is going up, therefore, it means that IRF is greater than ID, which in turn means that what comment can we make about Vg? No. What we should do is another matter. What does it mean first? Don't jump steps. What does it mean? Vg, it means that Vg is less than Vg star. Correct? I mean, basically means that if Vx is going up, it means that ID is much too small, which in turn means that the Vg that we have applied is not enough, right? So, what must I do? Must increase Vg. So, to summarize, therefore, if Vx goes up, I must increase Vg. All right. Now, likewise, if IRF is less than ID, what comment can we make about Vx? The potential Vx, the potential of the node Vx of the potential Vx of the node X will tend to fall, correct? And that basically means that the drain current, therefore, if Vx is falling, it means that the drain current is more than the desired one. So, that basically means that Vg is greater than the magic voltage Vg star. We must reduce Vg. So, if Vx increases, we must increase Vg. If Vx decreases, we must decrease Vg. All right. So, in other words, if this goes up, we must push Vg up. Okay. If X goes down, the gate must be pulled down. So, what is the simplest way of doing this? Short what? Well, the easiest way to do this is to simply short the gate to the drain. All right. Okay. So, in steady state, therefore, when the IRF will be exactly equal to ID, and therefore, the voltage developed at the gate is exactly that needed to make sure that the current in the drain is equal to IREF, irrespective of the properties of the transistor. Does it make sense, people? All right.